Hello there, a short version of the video on the strange behavior of the electron, or the introductory video into that matter. Now I think we all when we hear what is your first association when you hear the word electron? Well, I myself think of a little, maybe spherical party. Well, I myself think of a very tiny particle that is negatively charged, maybe even spherical, that moves around like a little charged bullet. Now we are in for a big surprise, because in 1927 the physicists Davisson and Germer made an experiment that was similar to the X-ray diffraction experiments that these guys did in the 1910s to understand the structure of crystals. But they didn't use electromagnetic waves, X-rays in that case, but a beam of electrons. So they shot an electron beam at a target. In the experiment that we are going to do, this is a thin graphite foil with a lot of graphite crystals in it, microcrystals. They back then used a nickel crystal, but that doesn't really matter, the result was about the same. So what would we expect? We have here a thin foil of graphite with a lot of randomly oriented graphite crystals, and if electrons really were tiny bullets, they would bounce off these crystals and would be scattered in all directions. So this screen here that lights up green whenever an electron hits it should be homogeneously green, right? Because the electrons get scattered in all directions. Well, we're in for a big surprise. We take a look. Okay, but before we take a look at the actual experiment, here is the voltage that accelerates the electrons that come out of this hot cathode that is being heated by a small voltage. This yellow stuff is simply to focus the electron beam. We are not going to talk about that much. And here's the anode lying on 3 to 5,000 volts of potential with respect to the cathode, and in the anode there's a small hole, and over this hole there's a very thin foil of graphite with a lot of microcrystals. So now, okay, buckle up and watch the experiment. So you can do, so I'll be damned. This is clearly an interference pattern. You can do similar experiments, for example, take a thin aluminum foil and shoot X-rays at it. You get something like that. And then use the same aluminum foil and shoot an electron beam at it. And you get that. Bam! Interference all over again. It gets worse. Because with electrons you could say, well, they are charged, they influence each other and do not bounce off in every direction equally. So this is why this pattern emerges. You can also use neutrons, which are neutral, of course. And you get this. And even worse, this is not a beam, a constant beam of neutrons. Those are neutrons fired at the, I think here it's a thin copper foil, one after the other, and still you get interference, and they end up on the screen as particles, as these small pixels or dots. Okay, let's take a closer look at the results of this diffraction tube experiment with electrons. Here is the electron gun. Here's the electron gun giving you a beam of electrons. Here is one graphite microcrystal, so here's the graphite foil, and this is an enlarged picture of one graphite microcrystal. And this angle theta 1 leads you to the inner ring that we saw. We saw actually two rings, but they are not the maxima of first and second order, but in the graphite lattice I have two lattice planes that can give me diffraction effects. One is if I look like that at these atoms, they have a distance d prime, which is 123 picometers, but I can also look in this direction, and then these layers or rows of atoms give me a different diffraction grating, if you want to call it like that. And here this distance is square root 3 times d prime, because of the hexagonal geometry of those graphite atoms, and this is 213 picometers. And this corresponds to the smaller ring, and we are going to work with the radii of the smaller rings. Because here's theta 1 and here theta 1, the reflected beam has an angle of 2 theta 1 that is going to be important later. So here are the actual results. If I take a voltage of 3000 volts, then the radius of this ring here is about 1.4 centimeters. It's hard to determine exactly, but these values will do just fine. Then the distance between the graphite foil and the screen is 13.5 centimeters. Here we make a little mistake because the screen is curved and we are missing this little distance here, but actually this doesn't matter much. So we simply assume that this also is about 13.5 centimeters. And then you do the same for 4000 volts and 5000 volts. And the radii get smaller and smaller. And now comes the important part. I have an interference pattern that looks about the same as when I use X-rays. So I simply try to use Bragg's law here as well. Here it is, the path difference of the electron wave beams, whatever that might mean, 2d times sine theta 1, this angle here, must be 1 times lambda, the wavelength associated to the interference pattern. And theta I can get from elementary trigonometry, as I said, with a little mistake here. So the tangent of 2 theta 1 is about R1 divided by A. I solve this for theta 1, plug it in here, and then I have a formula for a wavelength. Again, whatever this might mean for an electron. And this is calculated here. So you get wavelength in the picometer region, about the same as X-ray wavelength. This is big. That's why you get similar patterns here. And the most important column is this one. If you calculate wavelength times the classical momentum of the electrons that are shot at the foil, you get a constant. To get the momentum, you use the classical energy conservation law. Electrical potential energy of the electron here at the cathode gets completely transformed into kinetic energy when the electrons arrive at the anode. Then you get this velocity, and m times this velocity, and the momentum is m times this velocity, the mass of the electron. You can simplify it to this expression when you pull the m under the square root, and then you use the elementary charge of the electron and the mass of the electron, and then you can calculate this product, lambda times the momentum, and you end up with Planck's constant. And those are very good values. If you think about, remember that this was actually not easy to measure exactly, and that we are making a little mistake, this is a very, very good result. So, what can we conclude from this experiment? We must conclude that electrons can somehow display wave-like behavior, because an interference pattern is classically associated to waves, in the sense that they can generate interference patterns. And these patterns, or maybe the electrons themselves, we don't know yet, can be associated to a wavelength. I think this should be 2, not width, not sure. And a lot of further experiments also showed that this product here of this strange wavelength times the classical momentum always gives you this constant that Max Planck introduced 1900 or 1901 to explain the black body radiation, and which has since turned out to be the governing constant of the quantum realm. 6.63 times 10 to the minus 34 joule seconds. Now, where did this idea come from? Actually, 3 years before this experiment was done, a Frenchman named Louis de Broglie postulated that not only electrons, but every metal particle, so also protons, neutrons, mesons, which were known at that time, whatever elementary particles of matter there were, each one should have a wavelength given by this strange formula, Planck's constant divided by the classical momentum. He got this idea because for light, the same equation holds. We're going to talk about that later. And he coined the term matter waves, which is a very problematic and dangerous term that I'm avoiding. That I'm trying to avoid. It doesn't mean that the electron somehow is smudged over space and is oscillating like a wave. That's not true at all, and also not that the electron moves in like a sinus curve or whatever. We're going to have to very carefully discuss what this actually means, but from this experiment we can conclude that electrons, which we had in mind as classical particles, can also show wave-like behavior. That's all for today. Thanks for watching and bye-bye.